So my name is Dankers. I work at Wageningen Environmental Research. And my background really is more in the field of climate impacts on hydrology. And so many of the examples that I will show today will be from that area, but I think the general principles will also apply to other fields. So first, I wanted to reflect a little bit about the word impact. So what do we mean when we talk about impact models? Because this really will be different for different people. So I have worked a lot on flooding. And if I talk to climatologists and meteorologists, they will say that flooding is an impact of the weather or of the climate. But of course, if you're a hydrologist, then flooding is your main subject area. On the other hand, if you talk to a health professional, they will say that flooding is the cause of the impacts that they see in terms of health outcomes. So luckily, the IPCC provides some definitions, and I will not read it out here, but you can see it here. So I want to highlight that it's really, when we talk about the impacts, it's about the effects on lives and livelihoods of people, meaning health and well-being. It can also mean impacts on ecosystems and ecosystem services. And the other thing that I wanted to highlight is that impacts are the outcome, so the result of the interactions between hazard on one side and exposure and vulnerability. And I think we'll touch upon that a little bit more later on. So the IPCC also defines what they call physical impacts. So this really is about floods, droughts, and sea level rise. And when people talk about impact models, this is usually what they mean, but it is worth keeping in mind that what really matters to most people is the effects on health, well-being, etc. So why would we use impact models? Well, really, the main reason is that they allow us to provide more details on impacts of climate change on a specific sector. And usually, this level of detail is not provided by climate models. But at the same time, we have to acknowledge that climate models are evolving all the time and they become more complex. They develop into Earth system models, and many of the Earth system models nowadays, for example, they would also simulate things like fire. And they have to, because that provides a feedback to the climate system. But of course, it also means that they are straying into the territory of impact models. At the same time, impact models are also evolving and also become more and more detailed. So it's a little bit of sometimes a bit of a judgment with whether you can use the climate models to estimate your impacts or whether you really need to use an impact model. But often, if you look at a specific region or a specific sector, you're still likely to be better off when you apply an impact model. Impacts models have been developed for multiple sectors. So these includes waters and marine ecosystems, energy, forestry, crop production, biodiversity, human health, wildfires, and more. And if you want to get an idea, I recommend you that you check out the Intersectoral Impact Model Intercomparison project, and you see a link here. They have already a lot of impact model simulations available for all of the world, so you could use those for your study if necessary, and also it will give you an overview of the state-of-the-art impact models that have been developed in a particular sector. So impact models, they are often specific to a sector. This can be hydrology, this can be crop production. And often these models were developed with a different aim in mind. So many hydrological models, for example, were developed for operational hydrological forecasting. And only once these models were developed, people also started to apply them for climate impact studies. Sometimes models do simulate the same things. For example, many crop models will include also a representation of the water cycle. So there's an overlap between biological models, crop models, with the hydrological models, and vice versa sometimes as well. And impact models rarely give you the full answer. So if you're really interested in the human impacts, you usually are still required to do further processing of the output. You may do further analysis or even do further modeling to translate the physical impacts into, for example, economic losses. And this then gives rise to what you could call impact model change. So to translate your projection of climate change into a sectoral impact, there will be multiple steps. So you'll start often with the emission scenarios, global climate model simulations, often feeding into regional climate model simulations. Typically, you would then apply further downscaling or bias correction methods before you put it in, for example, a hydrological model. The hydrological model will give you then simulations of river discharge, and you may need to do further processing before you actually get into an assessment of your expected impacts for your region of interest, for your sector of interest. This is an example from a study a couple of years ago that aimed to show the same thing. So depending on your, what you actually want to do, there may be multiple models may be required to get to the answer that you want. So in this example, a paper by Meijin et al. From a few years ago, they used information about climate and they fed it into a hydrological model to calculate river flows, and then they used a hydraulic model to translate the river flows into water levels. And this information was then fed into an inundation model to actually simulate which areas might be flooded. And this information was then fed into a damage model in order to be able to calculate losses from flooding. So to get to your answer, what they were interested in, you need multiple models and multiple modeling steps. And this paper is quite interesting because they also looked at what uncertainty is introduced in each step. So if you're interested in that, I recommend you to check that paper out. Now I want to have a look at different types of impact models that are around. And we can start with really the most simple type of models, which I call statistical models. But really the idea here is that you establish a relationship between a weather or climate variable and your impact. And this is often done in, for example, the health sector. And the example that you see here is around mortality in relation to temperature. And you see two different places, London and Stockholm. Of course, if temperatures rise, you often see an excess mortality, so more people would die than you would normally expect due to the higher temperatures, and you see the same thing at the lower end, so on the cold end. And you can establish these relationships simply by using historical temperatures and statistics on mortality if these are available. And so based on past data, you can then establish a threshold temperature and the rate of increase, so you can then calculate your expected number of excess deaths due to a particular temperature. And you also see immediately that this will not be the same in every country or every location that you're looking at. So especially if you look on the cold side here, you see that the number of excess deaths in London is rising much faster than in Stockholm. And this is because people in Sweden are more adapted to cold climate, while in London there's often people are not so well adapted. There's often poor housing quality. And so you see that the relative risk, so the number of excess deaths, is increasing fast. So apart from using physical climate variables like temperature for establishing such a relationship, you may also be able to relate your impacts to, for example, large-scale weather pattern. And this then can also be used as a very convenient downscaling technique. An example from hydrology is a very simple, almost a black box model. For example, a transfer function that translates your effective rainfall. So this is rainfall after you account for losses due to evaporation and runoff. So this is a paper from quite a few years ago. But you can see the model that you used in the middle slides. It's just almost one equation that they used to translate rainfall into runoff. And then in this particular case, this is for a catchment in the USA. They found the parameters by optimizing them using over 100,000 Monte Carlo simulations. And if you do that, you see that you actually get a very good simulations of the river discharge. So it's possible to get very good fits if you use a method like this. So some pros and cons of these statistical or empirical models. So they're easy to understand and easy to run. Typically, they have low data requirements, and it's possible to obtain a good fit with historical data. On the downsides, they often will not give you very much insight into the processes, into the causes and the effects. And you have to be very careful with application outside historical conditions. So the key phrases here is really the historical conditions. It might be possible to use them in the future, as long as you are confident that you remain within the bounds of the historical conditions, or if you have good reasons to assume that the relationships will still hold. The target impact data may not always be available. So I showed an example of mortality in relation to temperatures. But if you want to look at, for example, hospitalizations, if the data is not available, it becomes more difficult to build a model on that. And this is especially true for many of the socioeconomic impacts. Think about damages and losses. And you have to be mindful that there's always a possibility of multiple predictors, spurious correlations, and so on. So you have to apply these models carefully.
Rutger?
Yes.
Maybe it's a good time for people to ask questions about the presentation so far. If you can go back one slide.
I can go back one slide, yes.
Maybe people have a moment to read the cartoon. So are there any questions so far?
It's worth reflecting that many of the what they call artificial intelligence methods are, often black box statistical models. It's worth keeping in mind. If there's no direct questions, feel free to ask them later on or put it in the chat, and then I'll.
What is pros and cons? So Sen writes in the chat. What is pros and cons?
Pros are benefits, so to say. Cons are downsides. So the pluses are the pros, the minuses are the cons. Okay. I'll proceed. If there are any further questions, I'll answer them later. Before moving on to the next type of models, I wanted to reflect that many of the more complex models contain submodels or process descriptions of process parameterizations that essentially are statistical models. An example I give here is snowmelt. So many hydrological models will calculate snowmelt based on a very simple relationship with temperature. So usually there's a threshold temperature, typically 0 degrees Celsius, and then they calculate the rate of snowmelt dependent on the temperature, how high the temperature is above your threshold temperature. And this is called the degree-day method of calculating snowmelt. But we know that in reality, snowmelt is a much more complex process. So there's all sorts of factors that influence snowmelt. There's the full energy balance, there's incoming radiations, there's the albedo of the snowpack, there's infiltration of meltwater, ground heat flux, sublimation from the snowpack, and all this affects your snowmelt rates, and all this is essentially ignored if you apply a very simple temperature threshold method for calculating your snowmelt. So the second type is what I would call conceptual models. So these are a little bit more complex. They include several...
Sorry, there is a question from Miku.
Yes, please.
In the chat. It says Snow 17 is a simple model.
Yes.
On the previous slide, I guess.
Yes.
Nico, what do you mean with Snow 17?
Yeah.
is a snow melt model. I think it's well known in hydrological modeling. Actually, it used some relation to parameterize the melting process, and I was wondering if it's considered a simple model or a complex one.
Well, but the reason why many people use such a simplified model is because it usually works really well, and the data requirements are not so high. You only need temperature.
Yes.
And if you look at the complex model, usually measurements of radiation, of sublimation, etc., are not available. So these, there's models that would simulate the full energy balance. We will have a look at those in a minute. But the data requirements are much higher. So it becomes more difficult to run them. And you do not always have these data available.
But we can perhaps answer this question later on, Jeanette, right?
Yes.
If this SNOW 17, that we look into this specific model, and maybe Rutger can say something about it later. Yeah.
Okay.
So the conceptual models. So these are a bit more complex, as I said. So they include several components. There will be storages and flows to mimic the most relevant processes. An example I give here is from a hydrological model, HPV, which is quite famous, has been around for over 40 years and has been applied all over the world. So the hydrological system of a catchment in this model is represented by a number of stores and fluxes, but similar schemes are also used in other models. For example, many crop growth models will use a simple tipping bucket model for soil water. And it's, especially in the case of hydrology, it's also worth making a distribution between what's called lumped and distributed models. So crop growth models, for example, usually do not take account of spatial interactions, but some other types of models do, like ecosystem models, especially if they intend to simulate the expansion of vegetation zones. But for hydrological models, this is usually very important. So lumped models are very simple models again, so they simulate the catchment as a whole, and you only simulate river flow at the catchment outlet. These models are therefore easy to parameterize or calibrate, and also very quick to run. And on the other hand, distributed models, which you see on the right-hand side, they usually account for all the spatial availability. Usually they're based on model grids, and they calculate the runoff at every grid cell. The downside is that input data are, input requirements are higher, and the model becomes computationally more expensive. And then somewhere in between, you have what people call semi-distributed models. So this is usually a set of nested lumped models for sub-catchments that make up your overall catchment. So distributed models, as I said, they account for spatial variability in the landscape and also for lateral processes. So this is important at some scales in our hydrological model in particular. And of course, nowadays, there's many spatial input data sets available, especially since the advent of remote sensing. So I give some examples here of hydrological models that are around, that are fully distributed, and I've worked with some of those myself, like the LISFLOOD model. You have to keep in mind that calibration is often only possible at the outlet of a catchment because you will not have measurements available everywhere. And also, at the scale of a single grid cell, you're still dealing what is effectively still a lumped model, and so the resolution matters. If you have very large grid cells, so some models have grid cells of tens of kilometers or more, especially if they're applied at the global scale, maybe the lateral exchange of water in the subsurface between grid cells is not so important. So some advantages and disadvantages of conceptual models. So the components resemble the main processes, the main characteristics of the system. So they're more robust than the statistical models. They can be used to gain insight into processes. scenario analysis, and indeed prediction. They're cheaper to run than the more complex process models that we will look at in a moment, let alone climate models. And they run typically at higher resolution, so you can use them to add detail. On the downsides, usually calibration is necessary, so you still have to be careful if you want to apply these models outside the historical conditions. Typically, if you are interested in human impacts, so human behavior and impacts, they are more difficult to model. And spatial data are not available for all the components, especially when it comes to the subsurface. So the third and last category of models that I want to look into is what I call process models. So these are more complex models, and they aim to include complete process descriptions following the laws of physics or biology, or whatever is relevant for your system of interest. These models were often developed to study the process and also the interactions between these processes. Often this means taking into account, for example, coupled land, surface, and energy, water balance, and the role of vegetation. So the example I give here is from NOAA, which is a quite widely used land surface model. And this tries to take into account all the relevant processes at the land surface. Usually, these models are actually a combination of different submodels for different components of the system. For example, there will be a separate model for snow and snow melt. There will be a separate model to account for soil moisture. There will be a separate model to simulate vegetation processes. And these are essentially coupled and combined into one model code. Also, not all modules may be completely physics-based. This is particularly the case for anything related to the subsurface and the groundwater. So even in these very complex land surface models, the groundwater system, for example, is often highly simplified and not resembling the physical reality at all. So advantages and disadvantages. So we have physics-based process descriptions. So these models are potentially even more robust than conceptual models. They include, or at least that's what we hope, all of the relevant processes, so we can use them to gain insight into the interactions between processes, between different components of the system. Some people would argue that they are less reliant on calibration and tuning, but in reality, even physically based models often include parameters that have been tuned to observations. But nevertheless, we can expect them to be more robust when we apply them outside of the range of historical conditions. But on the other hand, usually these models are rarely fully process-based in all components. They're computationally more expensive, they're more complex to run, and the data demands are higher. And this can also be a limitation. So you do not always have like all the meteorological input on radiation, humidity, etc., to solve the surface energy balance. If you compare them with conceptual models, often what you find is that they have less predictive skill than the conceptual models. And that's because the conceptual models, they are more abstracted, simpler to run, and they're easier to calibrate, and therefore they often outperform the more complex process-based models.
So are there any questions so far? Can you say something about the picture, Rutger?
Yes, it's about the laws of physics and the extent to what you are prepared to believe that they will hold.
No questions? Okay, please ask anything, all right?
Yes.
And you can also ask them in the chat, of course.
Yes. So I'll speed up a little bit because I think people are probably keen to have a break, but we have to keep in mind, so we have different models have been developed with different aims in mind. So hydrological models, for example, they aim to close the water balance of a catchment. Land surface models, often more complex, they aim to solve the energy and water balance of the land surface. Dynamic vegetation models, for example, they often aim to simulate the vegetation distribution and the carbon cycle. Crop models aim to simulate crop production, carbon and nutrient cycles, etc., etc. And especially land surface. Yes, is there a question?
I would like to ask about the distributed models. I'm afraid I didn't fully understood. So in fact, the fully distributed models, they solved some kind of equation relation in every point. So until some point, they are similar, let's say, to numerical weather prediction models, in the sense that they solve some kind of equation in each grid point or something.
That's right. Yes.
It's just they're simplified compared to process models, which do practically the same, solve the equation in each grid point.
That's absolutely right. So yes, a distributed model. So you see grid boxes here. They would calculate the water balance, if it's a hydrological model, for every grid cell. So they solve the equations for every grid box, while a lump model would only do that for the entire catchment. So many of the process-based models are indeed also distributed models. Numerical weather prediction models, indeed, are also distributed models.
Thank you.
Yes, most welcome. So yes, different models have different aims, so it's worth keeping that in mind if you want to apply one of these. Especially land surface models often try to include all the relevant components of the Earth system. I give an example here of JULES, which is a land surface model. So started off as an energy balance land surface scheme, but nowadays also includes a dynamic vegetation model, a crop model, an urban surface energy exchange scheme, a routing model for river discharge, schemes for irrigation, snow and ice. And that's really because it's a model that's used inside an Earth system model. So it has to simulate all of the relevant processes that are potentially relevant in terms of the climate and the feedback. I'll whiz through some examples of different models. It's a bit biased towards hydrological models, but this is a model that I've worked with myself. So it's called LISFLOOD, which is a spatially distributed hydrological model originally developed for flood forecasting. So the focus really is on the simulation of river discharge, but it can also be applied in climate impact studies, and I was one of the first to do that. Calibration is usually required, but there's also techniques to make sure that you can use, if there's no observations available, that you can use observations from a neighboring catchment, for example. And this model has been applied at relatively small size, so catchments that are relatively small with a grid size of, for example, 100 meter, to global, so grid size of half a degree, so that's roughly 50 kilometers. And it's actually, this model is also used as an operational flood forecasting in the global flood alerting system. So this model is freely available. You see the address there. And it has been used, well, as I mentioned, it's used for operational flood forecasting, but it's also used in climate impact studies. And the advantage is that you can include then scenarios of changes in land use and water demand. Because it's a spatially distributed model, it's sort of a hybrid between conceptual and process-based. You can, for example, then change your land use input map, and you can calculate the effects of that. And if you were only using a simple statistical lump model, this would have been very difficult to do. Another advantage is that you can then get spatially distributed output maps like the example that you see here. So you can get information on changes within your catchment. Was there a question?
Yes, there is a question from Letitia about, I think before you started with the examples, are there any models for the marine environment?
There are, but I'm not really familiar with those because I don't work in the marine environment. I gave the URL of the ESMIP project. I think it will come back at the end. So I recommend you to check that out because there is a marine sector in ESMIP, and they will probably, at the very least, list all the models that are available for the marine sector. The second example that I wanted to give, it's a model called LPJML. It's a dynamic global vegetation model for managed land. So it means it's specifically designed to also simulate crops. So this model was originally developed to simulate the terrestrial carbon cycle, but later expanded to also include the water cycle. and agricultural systems. The focus of this model is dynamics, crop production, and water resources. And again, this model has been applied at regional and global scale. And just as an example of the type of studies you can do this with this model, because it's a crop model that explicitly takes into account the water cycle, you can use it to look at the interactions between the water and the food system. So the example here is from a paper by Hester Biemans et al. From last year, where they looked at how much crop production in the Ganges and Indus Brahmaputra basins, depends on snow melt water from the Himalayas. And especially in the case of the Indus River in Pakistan, you see that this proportion is actually very high. So you would not be able to do this type of studies with a hydrological model, because typically hydrological models will not simulate crop production. But with a model like LPJML, you are able to do this kind of study. The third example is a model called JULES. So this is the Joint UK Land Service Exchange Scheme. So service model that developed to sit inside weather and climate models. So the original aim is to provide the boundary conditions of the land surface to the atmosphere. The focus really is therefore on simulating the energy and water balance, but it has been expanded to also simulate the carbon cycle, vegetation dynamics, nutrients, and much more. So this is a very complex model. There's many different modules and parameters. And often for one process, you have the choice of choosing different modules. So you can use a very simple model for snowmelt, for example, or a more complex model. And so in a complex model like this, people have developed what they call configurations. So this is a combination of parameters and submodels that performs best for a particular application. So this model sits, for example, inside an operational numerical weather prediction model, for which speed is important, but maybe not solving the water balance of a catchment. On the other hand, if it's applied in inside a climate model, then solving the carbon balance becomes much more important. A model like this can be applied at point scale, so you can compare it with observations at a single point, or at a regional or global scale. And again, it's available for free, and you can see the address there. And just to give some examples, this model has been applied for things like hydrological modeling, simulating vegetation dynamics, simulating crop growth under climate change, urban climate applications, and indeed also changes in permafrost, and also what, for example, decline in permafrost means in terms of carbon feedbacks to the atmosphere. So to close this section on impact modeling, I will go through some challenges that you may encounter. First is what I would call human impacts, and this can actually refer to two things. So first of all,
Rutger, may I interrupt a moment? There was a question from Dejan about DEM. What is the DEM source for LISFLOOD in the LISFLOOD model?
Oh, I think the LISFLOOD model can use different sources. So there is a standard LISFLOOD model set up for Europe, because it's used as an operational flood casting model in Europe. And it's a while since I used the model. I don't remember what the source is for the elevation data, but it's probably some standard European data set at 5 kilometer resolution. If you want to apply the LISFLOOD model for your own area of interest, you can use your own elevation data source if you have it at home.
So the DEM is related to elevation data?
Yes, so DEM is digital elevation model. Yeah.
Okay. Yeah. Okay. Thank you.
I hope that answered the questions. Yes.
Yeah. One thing, I propose you continue until your case study, and then we take a break.
Yes.
Yeah. Okay.
Okay. Human impacts, first of all, can refer to the impact that humans nowadays have on many natural systems, especially if you think about hydrology and river systems. Nowadays, many river systems are not natural. There will be reservoirs. Water will be used for irrigation. for flood protection measures. And these impacts can really dwarf the climate impacts. So the example on the left-hand side here is inflow and outflow into Lake Nasser in Egypt. So, of course, this is a very large water reservoir, and the outflow of Lake Nasser is completely regulated to meet the downstream water requirements in Egypt. So downstream of this reservoir, the river flow of the Nile doesn't resemble the natural flow at all anymore. And the other example that I give here is of the Aral Sea, which of course has completely dried up in over the decades because of water extraction in the upstream areas. So there are some models that try to take account of these human impacts, and the example that I give here is a model that is also widely used, is the water gap model. And without going into the details, but if you look at the flowcharts here, they really try to take into account of the global lakes and reservoirs in the river systems and the water withdrawals. And they model these withdrawals by looking at different sectors of irrigation, livestock, domestic water use. And often the data that they use these are based on statistics that are available for different countries. So if these effects are of interest to you, then I recommend you to check out the water gap model or similar models that are. Human impacts can also refer to the impact of climate change or environmental change on human systems. And earlier I showed an IPCC definition of impacts, and they mentioned that it's dependent on the interplay between hazards, vulnerability, and exposure, and that the impacts that are of interest to, in this context are usually in terms of socioeconomic impacts, the expected damages or losses. And the problem here is that the data on societal and economic impacts are often not routinely collected. So it's very difficult to get a complete picture of what, for example, the economic impacts of storms are. Insurance companies will collect data, but often only in terms of insured losses, so you'll not get a complete picture based on such type of data. If you want to model these type of impacts, there's also methods for doing that, particularly to model the vulnerability of your system. People use things like depth damage curves if you look at flooding. So this is simple statistical relationships between the inundation depth and how much damage that will mean for different types of land use, so whether you're in a built-up area, in an industrial area, or an agriculture area. Or you can use demographic and economic statistics as a proxy for vulnerability. So the example on the right here shows data for England, and they used a combination of socioeconomic indicators like how deprived an area is, what is the median income, to come up with some vulnerability indicators for how vulnerable the people are to flooding. And this type of data, of course, it's not direct, so they're particularly useful to compare regions against each other rather than giving absolute values. A second challenge that you may encounter is missing processes. For example, vegetation. So the vegetation response to climate change may affect your hydrological response, but many hydrological models will not take this into account, or only to a limited extent. So we already mentioned the impacts of a higher concentration of carbon dioxide. This will, for example, increase the water use efficiency of plants. So this is a process that is included in many land surface models, but not by many hydrological models. Another process that could happen is an expansion of vegetation zones. So you see a picture here, I believe it's from Alaska, or it could be Siberia, several decades apart, and you see that in the meantime your forest cover has expanded. So if you want to look at the long-term effects of climate change in some areas, and you are interested in the hydrology, you have to keep in mind that things like the vegetation may also change. A third challenge is what people call stationarity. So as we have seen, many models rely on calibration or tuning of the parameters. But actually, we have to ask ourselves whether these parameter values that we tune under historical conditions are still valid under very different climate conditions. So there's a whole range of literature around this problem, and it's a bit difficult to deal with. I recommend you to check out this paper by Metz et al. From a few years ago, which was one of the first papers to pay attention to this paper. But really, it could be a real difficult problem, but it will affect some parameters more than others. So some parts of the system will be more vulnerable to it than others. The techniques that you can apply to deal with it is, for example, you split sample tests where you divide your historical data into two different periods, and you test it. You develop your calibration method on one part of your data and you test it on the other part. You can try to include time varying parameters rather than simple static parameters. You can use covariates, and you can do a sensitivity analysis. But it's a difficult problem to deal with. And a third challenge is what I would call broadly model uncertainty. And one typical question is, which model do you actually want to use, or which formulation you want to use? There's often very different approaches that are available. Each of them will have their strengths and weaknesses, but sometimes they may yield very different results. And before I started my presentation, I think we already had a question around different models of evapotranspiration. So if you look at the graph here, you can see how different methods of calculating evapotranspiration will give very different projection of changes into the future. So the model formulation that you use does matter. And because it affects evaporation, it will then also affect your runoff estimates, for example. And what you often find, therefore, is that if you look at some of these intercomparison studies, that the impact model uncertainty adds to the overall uncertainty that you will get, in addition to that of the driving climate models. I think nowadays people will be aware that if you apply a range of climate models, you will get a range of outcomes in terms of simulated climate. But you have to be aware that the same may be true for impact models. And the example I show here is for river discharge in a number of river basins around the world. And if you look at some rivers, for example, the Ob here, the bar here depicts the range in changes in river discharge and that you get in an ensemble of 9 impact models. Each of these models was driven by the same climate model, and still some hydrological models will simulate an increase and some hydrological models will simulate a decrease in the future river discharge. So this highlights that in addition to the climate model uncertainty, the impact model uncertainty can also be important. So in the next 10-15 minutes or so, I would like to take you through applying a model, and the example I've chosen is a case study from Central Asia. So this is an ongoing project. It's far from finished, but what we want to achieve here is set up a model of the water resources in the context of food production in this area, which is very water scarce region, and we are focusing in particular on Uzbekistan. And the graphic here shows some of the components of the water system, the characteristics of the water systems. So there's obviously a lot of water coming from upstream, from the mountains, and it's being used in the downstream part, which is very dry, and there's a lot of water extraction in that part. So there's 2 main rivers here. They're called Sirdarya and Amudarya. They're transboundary river systems, so there's also a political dimension. As I mentioned, the water originates from the high mountains. So there's a large input from glacier melt and snow melt. There's at least potential for hydropower in the upstream parts. And the downstream parts are very dry, so they're highly dependent on the water from the upstream areas. And parts of this are very heavily irrigated. mainly for cotton production, but also for wheat. And over-exploitation of the water resource has meant that the Aral Sea has dried up, as we have seen before. So in this particular case, we wanted to use the LPJML model that I already mentioned earlier on, because we want to understand the link between, first of all, the sources and the use of water, but also between the water and the food system. So essentially, what we aim to do here in the end is to do something similar to what we did earlier on in the Indus Basin. And LPJML is also one of the few crop models that includes a complete hydrological cycle, including models for water management, which is very important in this area. However, usually the model is applied at global scales, so the data requirements can be a real challenge. And in the end, we want to use the model to calculate some scenarios of climate change, but also scenarios of different water management options, to see what the impact of those would be in terms of water scarcity, food production. So the typical process for setting up a model for a climate impact study would be, well, first of all, you start with determining the research questions that you want to address, and how and who will use the results will be used and who will do that. You decide on a modeling plan, and then you're selecting all the necessary input data, validation data that you may need. Sometimes you need to spin up your model. This is especially important if your model has very slow responding pools, as is the case for many vegetation models. You calibrate your model, or you may even need to adjust it. Some processes are not represented well. You evaluate the performance under historical conditions, and then typically you make a selection of climate models, and you run your model with these climate scenarios. You then have to post-process, analyze, and summarize your outputs, and then you still have to interpret the outcomes in order to be able to draw some conclusions. So there's many steps involved. And some of the problems that you may encounter, for example, it can be very difficult to get data that are specific to the region that you are modeling. So in case of Central Asia, we had a data set, so we know on irrigation canals. So for some areas, we know where the irrigation canals are, but you see here one area that's indicated in red. We know that there's also a lot of irrigated agriculture in that area, but our data set contains no data on irrigation canals. And even if we know where the irrigation canals are, we don't have statistics on how much water is being withdrawn, which areas are connected to these canals. So many data are missing, and in practice, you often will need a collaboration with local partners in order to be able to use local data sets if these are available at all. You could try to use global data sets, but then the quality is not always good enough. So I show here two different global data sets of part of the study area, and one global data set indicates the main land use category in this area is rain-fed croplands. Another data set indicates the main land use category is irrigated cotton. And we know it's mostly irrigated cotton in this area, so we know this one is better. But if you were to use this global data set, you're probably not using the right data set for this region. So again, you have to be very mindful of the quality that of the data sets that you use. If you are able to source the data sets, you'll find that there's sometimes mismatches. For example, in the vegetation classes or the soil classes that are in the data set, they may not match with what is used or needed in the model. So we are using LPJML. We know that cotton is important in this area. The data set that we decide to use, so it's the Merca 2000 data set of croplands, it has a class for cotton, but actually the model doesn't have it. The LPJML model uses something called crop functional types. So there's something like 24, I believe, available. but no specific one for cotton. So what do you do then? You can choose one that is closest in terms of its functioning, in terms of water use, etc. Or if you have unlimited time and of funding, you could decide to develop your own cotton crop type in the model, but of course that is more work. And another challenge that you will often find is that typically at some point you will run out of time and of funding, so you can only produce some preliminary results. So that is more or less the stage that we are now in Central Asia. Hopefully the work will still continue in the following years. But yeah, just to give you a taste of the type of results we do get at the moment, if you look at projections of river flow in one of these rivers, and we have run a model with two different climate models, we see that in using one climate model as input, we get an increase in river discharge towards the end of the century, and we use a second climate model as input, we get a decrease projected into the future. So we also get results that are not very clear. Of course, it indicates large uncertainty in the projected climate change in this region. But communicating this to, for example, local stakeholders can be a challenge. So some conclusions and recommendation, and this covers both the case study as well as the earlier part on impact modeling. So just to summarize, impact models, they can add more details on projected climate impacts in a particular sector and or area, and that is where they are used for most. They're easier to run and more flexible than the complex climate models that you have heard about. But you always have to be very clear about the impacts that you want to model. Are you really just looking at the physical impacts, flooding, changes in vegetation, or are you interested in economic losses or impacts on the human society? Be careful with applying models outside of the historical range, especially if these models have been heavily tuned or calibrated. And you have to ask yourself if processes that are potentially relevant or interactions that are potentially relevant are actually included in the model. And if not, whether the model is then suitable for your purposes. So keep in mind that more detail and or better performance in the past are, in principle, no guarantee for trustworthy future projections. So you can spend a lot of time setting up a model, let's say a hydrological model at very high resolution, and it will give very nice maps of projected changes, but it doesn't mean that these projections are more trustworthy than a coarser scale model. I would always recommend you to explore the uncertainty in relation to the model parameters. And you can, for example, use sensitivity analysis to see whether your parameters that have been calibrated are sensitive to changes in climate. Ideally, you would explore modeling uncertainty, for example, by not using a single model, but you can use multiple models. Of course, that's a lot of work, but then they may also be available from a project like the IS-ENES project that I mentioned before. So for many parts of the world, you don't need to set up a new model. There may be modeling results available already from the IS-ENES project. And in terms of communicating your results to the end user, I think always be clear about the assumptions that you have made during the modeling process, and also assist your user in interpreting the results, because you are experts when it comes to using the model, and they need your help in interpreting the results. And what I've seen in the past is sometimes people just present the outcomes of the model and say, this is what the model says, and and that's it. And sometimes you have to give some more context in order to assist your user. I think that is my last slide. So any further questions?